Hello everyone. In this video, we're going to learn how to solve quadratic equations using the quadratic formula. Previously, we have studied a universal method for solving such equations called the method of completing the square. And we know that that method is actually effective with any quadratic equation that can be put into this form. It may initially not be exactly in this form, maybe C is on the other side, etc. But as long as a quadratic equation, which by definition has a second degree term and a first degree term and a 0 degree term or a constant, is equal to 0, can have complex coefficients. Of course, we don't want a to be 0 because otherwise it will just wipe out this term and we get a linear equation. So the only restriction we put on it is that a shouldn't be 0, but the coefficient can be any complex number, and the variable here is also a complex variable. Now, for the purposes of this class, we will be dealing with real coefficients, but we will encounter complex solutions. But it doesn't take away from the fact that this method and this equation are defined for all complex numbers in the complex plane. So basically, the quadratic formula is a generalization of and can be considered to be a shortcut to the method of completing the square. So if we notice on the left here, we're just solving a quadratic equation by the method of completing the square. And if you recall, we basically get the square term and the first degree term, x term on one side and the constant on the other side, and then we proceed to get rid of any coefficient x squared might have other than 1 by dividing both sides by that coefficient to make sure that the coefficient of x squared becomes 1, because the process of completing the square that we discussed before requires that this coefficient be 1, and then we go ahead and find out what constant needs to be added to the square term and the first degree term in order to complete the square. And of course, we know that we have to take half the coefficient of the x term or the first degree term and then square it. So 1/2 of 3/2, of course, is 3/4, and we square it to get the expression to become a perfect square trinomial. And we of course have to add it to the other side as well. Then we simplify and we get it to a point where we can apply the square root property. And once we do, we're ready to go ahead and solve the equation. We're going to do exactly the same thing here on the right side, except instead of using any specific constants for a, b, and c, we'll just use the letters a, b, and c themselves to make this as general as possible. Notice that deriving a formula is another way of saying prove the formula. So basically, this will be considered a proof, which means we can henceforth use this formula with peace of mind, knowing that it should work because it has been proven. So we go ahead and start with the general quadratic ax squared plus bx plus c equals 0. Just like before, we keep the second and first degree terms on one side, move the constant to the other side, go ahead and divide both sides by the coefficient of x squared, just like we did here with 2, which is a here, the coefficient, to get rid of it and make the coefficient of x squared 1. So we end up with this expression. Now notice the coefficient of x here is b over a. So when we take 1/2 of b over a, of course we end up with b over 2a. And then in the second step of the process of finding how to complete the square, we have to square the b over 2a, and that's where we find this expression that we're adding to both sides. So then we know that this perfect square trinomial will factor in this fashion. it'll become the square of this binomial, and on this side we have this term minus that. I just wrote this one first because it'll look nicer. It's a positive term. Otherwise, this expression and this expression are exactly the same thing. So now we go ahead and get a common denominator. Of course, here notice that we're going to have to multiply the a by 4a, and we'll do the same on the top. So that's where we end up with the 4ac, and now both denominators are 4a squared. So once we do that, we can go ahead and make just one nice fraction here. And notice now, just like we were ready in this step here for the square root property, we are ready for the square root property here as well. So to go from this step to the next is justified by the square root property. Okay, so now we go ahead and apply the square root property, and we get x plus b over 2a must be plus or minus square root of all that, b squared minus 4ac over 4a squared. And we can go ahead and move the b over 2a to the other side by subtracting b over 2a from both sides. So we end up with x equals negative b over 2a plus or minus square root of, we can break this up, square root of b squared minus 4ac over the square root of 4a squared, which of course we know is just 2a. So since these denominators are the same, we can go ahead and combine the numerators, and now we get the familiar quadratic formula, which we all remember from our previous experiences with algebra. So the difference is, before we usually just used it, now we're actually proving it and we know where it comes from. It's simply a result of solving a general quadratic by the method of completing the square. So of course we realize these are two separate solutions written in compact form. So one of the solutions will be when we consider the minus case, the other solution will be when we consider the plus case. And these are our two solutions. So now that we have established this formula, we can go ahead and use it to solve any quadratic equation with complex coefficients. But do remember, in this class, we'll go ahead and deal mostly with real coefficients. In college algebra, you'll go ahead and encounter the complex coefficients as well. In this class, however, we will deal with situations where the solutions are complex. So take a look at this, make sure you're comfortable with this before we proceed. So just to summarize, here's the quadratic formula. If ax squared plus bx plus c equals 0, with a, b, and c being complex numbers and a not being 0 so that it doesn't reduce down to a linear equation, then x is going to be given by negative b plus or minus square root of b squared minus 4ac over 2a. Let's go ahead and try solving this quadratic equation using the quadratic formula, and we want to first of all make sure that it's in standard ax squared plus bx plus c equals 0 form, which this one is, so we can go ahead and proceed. So here we're going to extract the values of a, b, and c. We can see here that a is 1, b is 5, and c is 2. So as I will always recommend to you, if you're going to use a formula in any mathematics class, go ahead and write the formula without plugging anything in to begin with. Just write it down exactly as it is. So we get square root of b squared minus 4ac over 2a. It has two benefits when you do so. One is that, of course, after you write it down a few times, you're going to have it memorized with no problem. The second benefit is that you minimize the chances of making a mistake. So here we're going to get the opposite of b, negative b. B is, of course, 5, so we get negative 5 plus or minus square root of b squared, so that's 5 squared, which is 25 minus 4 times a, which is 1, times c, which is 2. The only one that's pretty safe to go ahead and do in your head is the b squared part. The rest of it just write out as you see it. and then we get over 2a, so that's going to be 2 times 1. So now we'll clean that up, so we get negative 5 plus or minus square root of 25. Now here we have negative 4 times 1 times 2, which is of course just negative 8. So minus 8 over 2 times 1 is just 2. So we end up with negative 5 plus or minus square root of 17 over 2. Now, just to make sure we understand that's two separate solutions, once we write our solution set, we're going to list it separately. Negative 5 minus square root of 17 over 2, comma, negative 5 plus square root of 17 over 2. And there is the solution set for this particular problem. And of course, just like the method of completing the square, we don't always depend on having simple, nice integral solutions. We can handle any kind of solution with this method. Make sure that you can handle a simple problem like this before we proceed. Okay, so here we have another quadratic equation that we're going to solve using the quadratic formula. This time we're not in the proper format yet, so we're going to take care of that first. So we'll go ahead and move the negative 2h squared to the left side to become positive 2h squared, and we already have plus 2h minus 7 on that side, and we're going to end up with equals 0 on the other side. So now we're in the proper format. We'll go ahead and write down the quadratic formula as is. So we get this time, of course, not x equals, but h equals negative b plus or minus square root of b squared minus 4ac over 2a. We jumped the gun a little bit. Let's go ahead and extract a, b, and c. A is 2, b is 2, and c is negative 7. All right, so normally I like to find that first, but this is okay too. So we get negative b, so negative 2 plus or minus square root of b squared, which is 4, minus 4 times a, which is 2, times negative 7, which is c. All of that over 2 times, this time 2a. So we get negative 2 plus or minus square root of, here we have 4, and negative 4 times 2 times negative 7 is going to give us a positive. We write that first so we don't forget it. And that's just 8 times 7, which is 56. And all of that will be over 4. So we'll go ahead and write negative 2 plus or minus square root of 60 over 4. If we look at the prime factorization of 60, we know that 2 goes into it 30 times, another 2 goes into it 15 times, then we move on to 3, which goes into it 5 times, and 5 will go into it once. So on the left here we have the prime factorization of 60, so we can see that there is a perfect square hidden inside it. So we go ahead and break the square root of 60 into 2 parts. We put the perfect square part in one radical, and whatever is left, which will be non-perfect square product, will go into the next one. So here we can see we can put 4 in the perfect square radical, and what's left is 15, which will go in the non-perfect square radical. And all of that again will be over 4. So now we're going to get negative 2 plus or minus 2 radical 15 over 4. And you know that in the spirit of good practice, we always like to simplify any mathematical expression as much as possible. Here we notice that if we factor out a 2, that will leave us -1 plus or minus square root of 15 over 4. Now we notice that we can safely and legally simplify those two to leave us 1 and 2. So we end up with -1 plus or minus square root of 15 over 2. So we can write our solution set now, and we're going to write it to contain these two solutions here. So -1 minus square root of 15 over 2 comma -1 plus square root of 15 over 2. So it's extremely important not to make a common mistake, which is to put parentheses around those, because that would indicate there's only one solution in the form of an ordered pair, and that never is used when you have only one variable. So we want to make sure that the reader understands that these are two distinct solutions for the same variable. You only use parentheses when you have two variables or more, so that your solutions are going to be in the form of an ordered pair or ordered triple, etc. So one other note is that sometimes you may see this solution written in split up format like this: -1/2 minus square root of 15 over 2 comma -1/2 plus square root of 15 over 2, and they're both correct forms of the solution set. And the last thing to note is that the order of these two solutions does not matter. You could put either one first and the other one second. Normally I put them in ascending order from the smaller one to the larger one, but that's not really important. It's just so that all our solutions look similar. That's the only reason we may want to do that. But otherwise, sets of this type are not ordered. So make sure you can handle a problem like this on your own as we proceed to the next one. So here we have another equation that needs some prepping first, because it's not in ax squared plus bx plus c form yet. So we'll go ahead and distribute the x here. We end up with x squared minus 10x equals -7. Now we'll go ahead and move the -7 to the left side, so we get x squared minus 10x plus 7 equals 0. So we're ready to extract the constants a, b, and c. We can see here a equals 1, b equals -10, and c equals 7. So we're ready to go ahead and write our quadratic equation or quadratic formula, which is -b plus or minus square root of b squared minus 4ac over 2a. And so we will go ahead and plug in. So first we want -b, which means the opposite of b. So b being -10, its opposite will be +10, plus or minus square root of b squared, which is going to be all of -10, including the negative squared, so that'll be +100, minus 4 times a, which is 1, times c, which is 7, all over 2 times a, which is 1. So we end up with 10 plus or minus square root of 100 minus 28 over 2. We'll want to simplify these as much as possible. So 10 plus or minus square root of 72 over 2. Let's continue on this side. So that's going to be 10 plus or minus. Now we're going to go ahead and simplify square root of 72. Let's take a look at it, see what it's hiding inside its prime factorization. So here's 72. We know 2 goes into it 36 times, 2 again 18 times, 2 again 9 times, 3 times, and again 3 1 time. So we can see it's actually hiding 2 perfect squares inside. That's 4, that's 9, so 36 is the largest perfect square factor of 72, and that leaves us a 2 here for the non-perfect square radical, and then all of that will be over 2. So we get 10 plus or minus 6 radical 2 over 2. Of course, we'll never leave it unsimplified, so we'll go ahead and factor a 2 on the top to leave us 5 plus or minus 3 radical 2 over 2. And this time we can see that these 2's will cancel completely, finally leaving us 5 plus or minus 3 radical 2. So now we're ready to go ahead and write our solution set, which will contain 5 minus 3 radical 2 and 5 plus 3 radical 2. And that's that. So it's possible that if you did it on your own, you may have left it a little bit early. Just make sure you simplify completely before you leave a problem. So if you haven't tried it yet on your own, make sure you write it down, see if you can carry through without getting any help, and then we'll proceed. All right, so here we have another quadratic to solve using the quadratic formula. We'll go ahead and put it in the proper format first. So we'll have u squared plus 10u. We'll bring the negative 34 over. It'll become plus 34 equals 0. Now we'll go ahead and extract a, b, and c. We can see that a is 1, b is 10, and c is 34. So we have u equals negative b plus or minus square root of b squared minus 4ac over 2a. You should definitely be trying these on your own before you come to watch the rest of the video for your own benefit. So we end up with the opposite of b, which is negative 10, plus or minus square root of b squared, which is 100, 10 squared is 100, minus 4 times a, which is 1, times c, which is 34, all over 2 times 1. So we have negative 10 plus or minus square root of 100 minus, okay, so here we have 4 times 30 is 120, 4 times 4 is 16, 120 and 16 gives us 136 over 2 times 1, which is 2. So we get negative 10 plus or minus square root of negative 36 over 2. And we used to say this is not a real number, but of course now we know what it is. It's a complex number and we can handle it now. So the only thing is we'll go ahead and break it up into 2 parts. Square root of 36 times square root of negative 1 over 2. So we have negative 10 plus or minus 6i over 2. We always go ahead and replace square root of negative 1 with its other name, which is of course I. Again, we notice that there's a common factor of 2 on the top, leaving us negative 5 plus 3i. and we have over 2. Again, we notice that we can cancel those 2's, and we end up with negative 5 plus or minus, left out a minus up there, make sure you put it back in, plus or minus 3i. So now we're ready to write our solution set, which contains negative 5 minus 3i and negative 5 plus 3i. And as you know, two solutions of this type, where these two terms are exactly the same, the operation between them is different, they're called complex conjugates. And that's what we have here. As I mentioned earlier, we will deal with equations that have complex solutions. We just won't be dealing with complex coefficients in this class. Okay, so that should do it for that one. So make sure you're comfortable with that before we proceed. Here's a really good one for you to try before you come back and join the video. All right, so I'm assuming you're back. Welcome back. So x minus 12 equals, we're going to go ahead and multiply this out. So we get 2x squared minus 6x plus x minus 3. So we get x minus 12 equals 2x squared minus 5x minus 3. Before you start moving things around, make sure you have fully simplified each side. That's the best practice and the one leading to the least possible chance of error. So now we've simplified both sides. We'll go ahead and move everything to the right side. So we have 0 equals 2x squared minus 5x minus 3 minus x plus 12. I know that some of you are used to always taking your variables to the left side, but there's no such mandate. So we get 0 equals 2x squared minus 6x plus 9. Okay, so now we're in the proper format. We're ready to go ahead and plug into the quadratic formula as soon as we determine a, b, and c. So we can see here a is 2, b is negative 6, and c is 9. So we go ahead and write down our quadratic formula always as is without any substitution to begin with. So we get negative b plus or minus square root of b squared minus 4ac over 2a. So the opposite of negative 6 is 6, plus or minus square root of the square of negative 6 is 36 minus 4 times a, which is 2, times c, which is 9. All over 2 times a, which is 2. So we end up with 6 plus or minus square root of 36 minus 72. 8 times 9 is 72 over 4. That was a terrible fraction line. Let me try that again. So we end up with 6 plus or minus, now we know 36 minus 72 is actually square root of negative 36. So here it looks like we're going to get complex solutions again. So we have 6 plus or minus square root of 36 times square root of negative 1 all over 4. So that's 6 plus or minus 6i over 4. We notice we do have a common factor of 2 on the top, leaving us 3 plus or minus 3i over 4. Now that 2 and 4 are both free factors, we can go ahead and reduce them to 1 and 2. So now we have 3 plus or minus 3i over 2. Now, it's okay to leave the solutions like these, but usually mandated and preferred that you go ahead and put them in standard a plus bi form. So to get that, we're going to go ahead and break that up as 3/2 plus or minus 3/2 I. Now we can write our solution set to contain 3/2 minus 3/2 I and 3/2 plus 3/2 I. And that's all there is to it. So very, very simple, just kind of tedious. It's very important that you distinguish between difficult and tedious. Difficult is just a hard nut to crack, you know, it's like a problem that you have to come up with the equation yourself, etc. But tedious just means there are lots of steps, lots of little details where things can go wrong, etc. So I would say this process is leaning toward tedious, but certainly, as you can see, not difficult. So make sure you can handle that, and we're going to move on to another one. All right, so if you were with me for the last video where we handled problems using the method of completing the square, you would remember this problem as the last problem that I had put up in that set. And I left that there for you to solve using the method of completing the square, but not before I gave you the trick, which is to clear the fractions first, because that makes life a lot easier. So this time we will go ahead and solve it using the quadratic formula. So we're going to go ahead and multiply both sides of this equation by 12. And when we do so, we want to make sure that we remember to distribute. So the 12 will get distributed by all three terms here. So we get 12 times 1/2 x squared plus 12 times 1/3 x. Always challenge yourself and try to do this on your own before you come to watch the way I do it to see if our answers agree. That's the way you learn mathematics, by participation. And we get 12 times 0 on the other side, which is 0. So here we can cross cancel now to clear the fractions. We get 6 here, we get 4 there, and we get 3 here. So our new simplified equation is 6x squared plus 4x plus 3 is equal to 0. It's a very nice simple equation. So we have a equals 6, b equals 4, and c equals 3. Once we've extracted those, we'll go ahead and write down the quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac over 2a. And now we'll go ahead and substitute. So the opposite of b will be the opposite of 4, which is negative 4, plus or minus the square of b will be the square of 4, which is 16, minus 4 times a, which is 6, times c, which is 3, all over 2 times 6, which is a. All right, so we have negative 4 plus or minus square root of. Now, if this kind of subtraction usually gets you in trouble and you run into errors, no instructor at this level is usually going to care if you do that on a calculator. So feel free to do that, at least in my class. But again, if your instructor is picky on that, your own instructor, certainly don't do it. But if you're in my class, then we have no problem with that. So we can go ahead and just type in 16. We can type in the entire radicand, and we'll get to know that radicand more closely soon. It has a special name. It's called the discriminant. So we get 4 times 6 times 3 and that gives us negative 56. So we get negative 56 here over 12, and we have negative 4 plus or minus. We're going to go ahead and simplify that. So let's break it into 3 radicals this time because of the negative. We'll go ahead and reserve the last radical for the negative 1. 56, if we take a closer look at it, we have 2 goes into it 28 times, 2 again 14 times, 2 again 7 times, and 7 1 time. So once we get to 1, we're finished with the process of prime factorization. On this side, we have the prime factorization of 56, so 2 times 2 times 2 times 7. We can see that there is one perfect square that we can bring out, so we'll put that here, the 4. So this part is not going to be any perfect square involved, so we go ahead and multiply those to get 14. That will go in here, and so we have negative 4 plus or minus 2 radical 14 I, make sure you don't put the I under the radical, over 12. So we have, notice that we can factor out a 2, so we'll do so. So we have 2 times negative 2 plus or minus radical 14I all of that over 12. Okay, so we notice we can cross cancel the 2 and the 12 to leave us a 6 down here. So we have negative 2 plus or minus square root of 14I all over 6. Remember that we want to put that in standard complex form, so we get negative 2/6 plus or minus square root of 14 over 6I, and we notice more simplification possible here. We're left with 1 and 3. So finally we have negative 1/3 plus or minus square root of 14 over 6I, like that. So we'll go ahead and write the solution set, which should look familiar again if you were with me for the last video. So we get negative 1/3 minus square root of 14 over 6I, and comma negative 1/3 plus square root of 14 over 6I. And that should wrap it up for this problem. So that's a good problem. It's usually not the algebra that gets people, it's the arithmetic. So make sure you can handle the arithmetic before we move on to the next problem. That's usually also the case as people move on to calculus. Like, for example, it's not usually the calculus concepts that gets them, it's the algebra and the trigonometry that gets them. So make sure you have these 2 courses really solidly down before you move on to higher math. All right, if you remember, I mentioned earlier that we're going to get to know this expression that you see under the radical here, formerly called the radicand. We call the expression under a radical the radicand. Now, the radicand of the quadratic formula actually is an important number. We call it the discriminant because it helps us discriminate or tell the difference between various types of solutions for a quadratic equation of this form. Now, in particular, now remember that we said that these quadratic equations can be solved by this formula even if the coefficients are complex. But if we limit ourselves to what's really common, which is that the coefficients are actually integers, then some interesting results come out of the discriminant. Now, if we call this expression b squared minus 4ac d, or we usually use capital D for discriminant, then notice that if a, b, and c are integers, when you look at this expression here, which gives us the values of x, well, that means that's going to be some integer. That's going to be some integer, because remember, 2 times an integer is just another integer. So the only thing that could change this from being some kind of an integer over integer, or in other words, rational situation, will be this expression here. So that's why that expression plays such an important role, because these two are pretty solid players as far as keeping things in the rational zone. So we just need to worry about that. So it turns out that if the value of d meets certain criteria, then we can make some conclusions, which we'll go over now. Now, if d happens to be positive, notice that means we have a positive number under the square root. Remember, we're dealing with a, b, c being integers. So now, if on top of being positive, it's also a perfect square, that means we have the square root of a positive perfect square. So that's just going to be a nice whole number, and we add it or subtract it in this manner, and we end up with 2 rational numbers for the solutions, because we get integer on the top, integer on the bottom. We know what that means. We don't need to worry about a being 0 anyway, so we're not going to get 0 in the denominator. So we end up with what's called 2 unequal rational solutions. Unequal because, of course, you get a different thing when you add a positive number to negative b over 2a than when you subtract the same positive number. That's why we have the unequal written here. Now, as it turns out, sometimes various disciplines, mathematicians, physicists, etc., they don't need to actually solve an equation to get important information from it. All they need to know is to know what types of solutions that equation has. And this process of just calculating the discriminant is ideal because it's such a simple expression to evaluate. So that's why we care about the discriminant so much. Now, one of the nice things that you can tell when this happens, when you get a perfect square under the radical, is that this expression here, which is basically the left side of the equation, is factorable. So that means if this happens, that means you could have solved the quadratic equation using the method of factoring, which we had discussed previously. Now, if d is positive but not a perfect square, remember, we've discussed this previously, the fact that the square root of a non-perfect square is always irrational. So we're going to end up with 2 unequal solutions again, because we're adding or subtracting a positive number, and they always end up being different things, but this time they'll be irrational solutions. And when this happens, we know that this expression here was not factorable. So we would have to either utilize the method of completing the square or the quadratic formula to be able to solve such an equation. And the third case is when d is 0. Now, if d is 0, the square root of 0 is just 0. It doesn't matter whether you add 0 or subtract 0. You're going to get just one answer, which is negative b over 2a. And that's going to be our only solution. And of course, since this is an integer and this is an integer, that'll be a rational solution. So we call that a rational double solution, because basically what that means is you had a situation such as here, x squared minus 6x plus 9 equals 0. Notice that can be factored as x minus 3 times x minus 3 equals 0. So zero factor property tells us x minus 3 is 0 or x minus 3 is 0. So notice we end up with x equals 3 as a solution twice. So that's what we mean by double solution. Another way of saying this is that this is a solution of multiplicity 2. Another name for a solution of an equation is called the zero of an equation. So we can also call it a double zero. Yet one more name is root. So we can also call it one rational double root. All of those work. Now, the last case is when this becomes negative. Of course, when that becomes negative, you're taking the square root of a negative number. We know what that means. That means you're going to have complex numbers coming out because there's going to be an I involved. And of course, you're going to get a minus bi and a plus bi. They'll be exact, of course, not this a and b. Let's use capital A and capital B, for example. But they'll be exactly the same except for the sign between them. That's why we say they're two complex conjugate solutions or roots or zeros. And this again means that this expression here on the left side would not have been factorable over the set of integers. Of course, you'll find out in college algebra all quadratics are factorable, except they're not factorable. The ones when we say no, we mean over the set of integers. So they're not factorable in an easy way, x minus 5 times x plus 2 or something like that. You can still factor any quadratic if you allow complex numbers to be the constants that you subtract from x. But again, more on that in college algebra. So simple stuff, important. Make sure you stay on this page, pause it until you understand it before we move on to look at some examples. So we've arrived on our last screen of material. Yes, huh? Okay. All right. And here we are going to look at some quadratic equations. They should look familiar to you. Do they? We've seen all three of these before, and I just worked this one out for you in the previous screen. So we've seen them all before. So the only thing is we're going to try to just look at them and determine whether we have real solutions, complex solutions, etc. In other words, we're going to determine the number and types of the solutions without solving, without actually solving. So if you were to solve these, that would kind of be cheating. So we want to just use the discriminant. And why would you want to do that when it's so much easier to just look at the discriminant, right? So let's go ahead and make sure that, first of all, they're all in the proper format. Because remember, to use the discriminant using the analysis we just did, we have to have not only ax squared plus bx plus c equals 0 form, but we also have to make sure these are all integers before we can use the discriminant analysis we just did. So in this case, we notice this one is good to go. So we notice we just extract a, b, and c. A is 2. B is 3, and C is 1. Remember, all we're calculating here is D, capital D, which is B squared minus 4AC. So now we substitute, so we get 3 squared minus 4 times 2 times 1. So we get 9 minus 8, which is 1. Now, 1 is obviously both positive, I mean greater than 0, and also we know that 1 is also a perfect square. Of course, it's a perfect square of 1 itself. So this is the category where D is greater than 0 and D is a perfect square. And if we look back real quickly, you will see when D is positive and a perfect square, we're going to get two unequal rational roots or solutions. And this means it's that the expression on the left was also factorable. So we have two unequal rational roots. And yes, it's factorable. meaning this expression, because that's what they asked. Once you put it in this form, is that part of it factorable? Of course, you can quickly factor that. Look, you have 2x squared plus 3x plus 1 equals 0. So if you just go with 2x plus 1 times x plus 1, that should get you there. And notice first times first is first, last times last is last. Inner and outer products add up to the middle term. So if you just set each one of those equal to 0, notice this is not part of the problem. I'm just demonstrating. Do not do this if you're asked to solve this, but I just wanted you to see and gain some confidence into the method. So you get that. So notice two solutions, -1/2 and -1. And of course, they are two unequal, and both of those are rational numbers. So I'm going to do a better job on the -1/2 and also on the -1. All right. So that's how we do that. For the next one, go ahead and make sure that you try it on your own first. Put it in the proper format, which is this, and then proceed. So we have x squared minus 10x, and I'm going to bring the -7 over. So plus 7 equals 0. So we can see that a is 1. B is -10, and C is 7, now that we're in the proper format. So now we can calculate D, which is B squared minus 4AC, and we have -10, quantity -10 squared minus 4 times A, which is 1 times 7. So we get 100 minus 28, which is 72. And 72, of course, is greater than 0, but 72 is not a perfect square. So if you recall from our previous screen, that means it falls into this category. So it's positive, but it's not a perfect square. Because it's not a perfect square, the square root of a non-perfect square ends up being irrational. So we're going to get two irrational solutions from that equation. And we've already found them earlier in the video. And as far as factorability of the ax squared plus bx plus c part is concerned, we of course know that that falls into the no category. So that's how we will go ahead and classify this particular problem. So it is, we have two unequal irrational roots or solutions, and the expression on the left will not be factorable. Of course, the expression after we've put it in this form. And that's how we would classify this one. All right, for this next one, remember in its current format, we can't use the discriminant law we just discussed or the rules. We have to make sure these are integers first. So just like we did when we actually solved it, we do need to go ahead and clear those fractions. So we'll multiply by 12, and that'll be by all terms because of distribution. So if you recall, we end up with 6x squared plus 4x plus 3 equals 0. So we have A equals 6, B equals 4, C equals 3. So the discriminant will be B squared, which is 4 squared. Let me actually write down the general form so we stick with our consistency. So b squared is 4 squared minus 4 times a, which is 6 times 3. So we end up with 16 minus 72, which is a negative number. I know that much, but let's go ahead and calculate it. If I recall correctly from when we did it, that should be negative 56. Let's make sure that's 12. Yeah, so negative 56. Now we can see that this is negative. So what that tells us is that we're going to be in the category we discussed here, which is two complex conjugate solutions. So, and we've already seen those two complex conjugate solutions if you look back in the video. So therefore we get two complex conjugate solutions, and remember, this is another one of those which is not going to be factorable. All right, the last example we have, we can see that it's in proper format. A is 1, B is negative 6, and C is 9. And here we're going to get D equals B squared minus 4AC. So we're going to get quantity negative 6 squared minus 4 times 1 times 9. So we're going to get 36 minus 36, which is 0. 0 is, of course, a perfect square, but it's not positive, so you're not going to end up with two unique solutions. You're just going to get one solution, which, as you saw in the previous screen, let's go back real quickly. What that means is that you get the same solution twice. That's why it's called a double solution. And of course, they'll be rational because they'll just be negative b over 2a. So here we'll say, therefore, we have one rational double solution. As far as factorability of the expression on the left is concerned, we already saw in the previous screen that of course it is factorable. It's just x minus 3 times x minus 3. But more importantly, keep in mind that if we go to our previous screen, anytime you have a perfect square situation, whether d is positive or 0, remember 0 is also a perfect square, then the expression on the left, the ax squared plus bx plus c part, will be factorable and your solutions will be rational. That's the easiest way to understand and apply that. So of course here this expression will be factorable as well. And that should pretty much do it for today. So make sure you practice plenty of these and be safe until we meet again.